We will be starting essentially something called parametric equations today, and plane curves and parametric equations. So essentially, parametrics are when we define x and y separately with another variable. So you're graphing on the xy plane, but you have another variable that influences what the coordinates of x and y actually are. Usually, that variable is going to be t for time. Everybody good so far? So when I write a parametric function, I don't write just x of t. I'm going to have two different functions that define it. One that defines the x coordinate and one that defines the y coordinate. So let's say I wanted, so the first one we're going to do is just, we're going to let x equal t squared minus 4 and y equal t over 2. And we're going to do this for the values of t that are in between -2 and 3. Okay? So if I wanted to find out what is x when t equals -2, or for those for any of those values, what I want to do is plug -2 in for t. So this x would become -2 squared minus 4, which is something? 0. Thank you. All right. And if we kept this going, what would we get? -1 squared minus 4 is -3, yeah? -4, -3, 0, 5? Does this make sense so far? Okay, and for y, we would just cut each of those in half, so we'd get -1, -1/2, -0. That's, you guys pretend, we're all going to pretend that didn't happen. 1 and then 3/2, yeah. Everybody good? All right, now, what we like about parametric equations is they can also tell us when we were at a certain point. So for instance, this function, so like if I want to let's graph the function first. So if I want to graph this function, if I want to write the point for t equals -2, that point is at the coordinates 0, -1. Do you guys see that? And then -3, -1/2. And then 0, then -4, 0. And yeah, okay, I'll fix that. I didn't look at my scale. I screwed up the -3. Everybody good? And then -3, +1/2, 0, 1, and 3/2. Or 5 3/2, excuse me, which would be way over here. How are we feeling? Is this okay? And so then we can say, okay, like we actually have, if we look at, say, this point right here, if I wanted to ask you guys, when did that point happen? Depending on however we define t, that could be, oh, that happened after 2 seconds. Because that point happened when t equals 2. So we can take a coordinate and it adds in a time component if we wanted to think of it that way. And because time travels in a positive direction, as we go to sketch this curve, which you guys, this is a very poor sketch of a parabola, this curve actually has direction. So when we talk about plane curves have an orientation to it, a direction to it. Now, how are we feeling so far? Is this okay? All right. Now, if I wanted to, so this is a parametrically defined. When we deal with just x and y, we call that a rectangular equation. So up until today, every equation you ever graphed was a rectangular equation. And when you think about that xy plane is basically rectangular coordinates, right? Like the distance between any coordinates is defined by a rectangle. Okay? So now, the rectangular equation, if we wanted to turn this into a rectangular equation, so we have x equals t squared minus 4. And are you guys cool if I say 2y is equal to t, if I rearrange this equation? Okay. And so then, if I want to find the rectangular equation, you solve one equation for t, and then plug that value for t into the other equation. So like if I do this one, we get x equals 4y squared minus 4. Now, can we type this one into our calculator to come up with the graph? We'd have to rearrange it, and could we do it with one function? No, we would need a plus or minus eventually, yeah? So we could do the positive side, so if I arranged this and got the y by itself, but didn't use the plus or minus, I'm only going to get this part because it's only going to graph that positive square root. Is everybody with me? Okay. Your calculator can actually graph parametric equations. You've just never done this before. So I want to show you guys how to do that real quick. So if you guys could please take out your calculators. All right, so if you could, go ahead and hit the mode button. Right here. It's next to the second button. And you'll notice right now your calculators have this like function, parametric, polar, and sequential. Those are all different modes. We're going to just put our calculator into parametric mode. Everybody good? All right, and then now if we wanted to graph our equation, normally with graphing we have to hit the y equals button, yes? Hit that y equals button. And notice now it's asking you for x equals and y equals. So for x equals, I could do t, and it automatically shifts that variable to t. And t over 2. You guys with me? And then I'm going to go to hit the window. And you notice where it's asking me for my t min and my t max and my t step. Okay? My t min, I'm going to make -2. My t max, I'm going to make 3. And I'm going to make my t step 1. And what's that? And the reason I did that is my minimum t, my maximum t, and the steps in between are all one unit, right? Okay, and now when I do this, making sure my x min max, we'll make this 0 and this 2, just thinking through. Oh, no. My y min needs to be -2 to 2. My x's go from 0 to -4 to 5. Something like that. Okay, so now when I hit graph, now, is that what yours looks like? The window's slightly different? Yeah. But is it pointy like this? Yeah. Okay. Why is it pointy?
We turned down the step.
Because of the t-step, because it's really only plotting the 5 points that we found in connecting them. So let's go ahead and say, well, what if in that window I change my t-step to 0.5? It's smoother. It's still a little jagged, right? But do you guys see what's going on there? Okay? And if I did 0.05, it's starting to smooth out quite a bit, right? And did you see how it did it in time? Okay? Did you see where it started? It started at the lowest t value. Are we feeling okay so far? All right. So one thing I might ask you to do is graph these parametric equations, okay? And then the other thing I'm going to ask you guys to do is find the rectangular version of the parametric equations, which is essentially what we just did, yeah? Okay, so let's go ahead and go to our rectangular equation was the x equals 4y squared minus 4. That's fine. Because like part of the goal of the parametric equations is that you can graph both. Graph both x equals and y equals. Everybody good? Okay. Page.
Real quick, if you ask us to find the rectangular equation, do we have to get it all the way simplified to like y equals plus or minus?
No, you can. It can be in terms of x or in terms of y. I don't.
So as long as you just have.
So for instance, when we did this one. Oh good. I even have this corrected. All right. So you guys, for this one, let's go ahead and do an XY table like we just did, kind of, right? And let's go ahead and let our t-step be 1/2. Is that okay? So we're going to start at -1 for t and go up by 1/2 each time.
Wait, but isn't that not in the
You always do this. Which is why t is greater than -1. So yes, these are undefined. Can you guys see if I'm standing here, by the way? Okay. You guys, can you guys fill out the table? Since you have the functions for x, you have the functions for y, you have the values for t. Decimals are fine. Is this what you guys got? Copying my stuff from earlier, just so yeah. Okay. All right. So when t equals -1/2, we have the point 1.4, -1. So roughly here, yes? This is good. And then 1, 0. And so I kind of like to do like my directional, because the direction of that is kind of an interesting component, okay?
How do we know?
As t increases. So you start with your lower values for t. And then 0.8, 0.3. And essentially it starts looking like this. How we feeling? All right. Okay, so that's one thing I might ask you to do is graph the function. The other thing I might ask you to do is find its rectangular equation. And to find the rectangular equation, what we have to do is solve one of these two things for t. Now, we can either solve x or y, doesn't matter. Which one do you guys want to do? Which one do you think would be easier? You did x? I think x would be a little bit easier only because there's only one t in the x. And so if I take x equals 1 over the square root of t plus 1, what's my first step to getting that t by itself? Multiply over. So I'd get the square root of t plus 1 equals x times the square root of t plus 1 equals 1. And then, so the square root of t plus 1 equals 1 over x. Very good. And square both sides. Subtract 1. So t equals 1 over x squared minus 1. So then I take my y equation. Plug that in for t. Everybody good? What I would probably do from here is multiply both the top and the bottom by x squared. And I would get y equals 1 minus x squared. Because everything else would cancel. Yeah? And you guys looking at this parametric curve, does this look like y equals 1 minus x squared? Negative x squared, opening down with a y-intercept of 1. That's about what this looks like. How are we feeling, okay? All right, let's look at another one. Oh, sometimes we might use parametrics to just define parametrically using trig, and some lovely things start to happen here. So here, if we're doing that table, we're going to have a theta, an x, and a y, and we're going to define theta using angles, okay? So, and I even tell you to go from 0 to 2 pi for your angles. And for sine and cosine, I don't know about you guys, but I kind of want to do like let's do 0, and then pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. So we're making our theta step pi over 2. If we kind of think of it that way, yeah. Cool. And you guys, what is 3 cosine of 0? 3. What is 3 cosine of pi over 2? So I specifically chose the angles on that unit circle that are these ones to make it relatively easy to... You guys, what's the sine of 0? 0. What's... All right, and 4 sine of 0 would be 0. What's 4 sine of 0? Or 4 sine of pi over 2? Okay. Are you guys with me so far? This doesn't feel that bad, does it? Cool, let's graph it. 3, 0, and then the next point, 0, 4. And then the next point's negative 3, 0, then 0, negative 4, and then 3, 0 again. Could we add more points in the middle if we wanted to? Here's what it's going to look like. Not a circle. An ellipse, because the...
Oh, yeah.
It almost feels like you're going around the unit circle with an ellipse. It's just like, oh, I need to get a little bit further on the outside now. Is everybody good? All right.
Wait, so you go from the little values to the, yep, okay, got it. It's like, why does it look good? That was worse than I heard. I'm not saying mine.
And but like if we would have done like 0 pi over 4, pi over 2, 3 pi over 4, right? Had we done that, we'd have those intermediary ones that would...
Mine kind of has some diagonals going on.
It's fine. Okay, you guys. So next what we need to do is find the rectangular equation.
Sorry. Do we need to take like the inverse?
Sure. So are you guys with me that if x is equal to 3 cosine theta is equal to x over 3, and theta would be equal to the cosine inverse of x over 3. And so then y would be equal to 4 times the sine of the cosine inverse of x over 3. Feeling okay? How do...
To like graph this, because I know the like x button, it has x, t, theta, and n. Like, is the theta for like this situation?
No, the theta is for what we're doing next week.
Yeah. This is
Well,
theta.
I don't know if we'll get to it next week. Theta is for polar coordinates, which is where we're going after we do parametric stuff. Okay, you guys, now we got to kind of turn this into a function. So let's see, if cosine theta equals x over 3, does this picture feel okay?
Yeah.
Making this the square root of 9 minus x squared. I'm hoping that we feel pretty confident with these kinds of things after last unit. Okay? So, essentially, we want to find the sine of this angle. So are you guys with me that y would equal 4 the sine of the angle would be the square root of 9 minus x squared over 3.
So because we use the inverse cosine of x over 3 to make the triangle, we can just say what is the sine of that triangle? Okay. Cool.
And I don't know, this feels a little icky. I'm going to rewrite this as 3/4 y equals the square root of 9 minus x squared. And when I'm done, you'll see why this feels icky. Okay? Then what?
Split the square root.
Just square both sides to get rid of the square root. Is everybody good? So we get 9/16 y squared equals 9 minus x squared. And then you guys aren't running out of space, are you? That would be x squared plus 9 over 16 y squared equals 9. And then if I divide that through by 9, I get x squared over 9 plus y squared over 16 equals 1. And now we have, in fact, the equation of an ellipse. Which is kind of where we start, like, from what we did yesterday.
Wouldn't just like stopping at like the y equals originally, like isn't that still correct though for the rectangular function?
So anyway, this feels pretty icky, doesn't it? There is an outside way of looking at it if we wanted to that doesn't feel nearly as icky. Everybody good? So we already wrote down that cosine theta is equal to x over 3 and sine theta is equal to y over 4. Are we comfortable with those two things? Hey, do you guys remember a very cool trig identity that is the Pythagorean identity? You do. What's the Pythagorean identity?
Squared plus y squared equals
Sine squared plus cosine squared equals 1. If I apply sine squared plus cosine squared equals 1 to this particular equation,
That's really convenient.
what would sine squared theta be? Y squared over 16 plus cosine squared theta, x squared over 9 equals 1. So to answer your question, I think when you graph it and recognize it's an ellipse, I think it's reasonable to expect that you write the standard form of the equation of the ellipse, which is why you had to learn the standard form of the equation of the ellipse. That being said, I'm not evil. I'll show you the shortcut to get there.
Can't you also get that from the graph?
Yeah, but isn't it cool how it all works out?
But
Like, I think that's pretty darn special. Yes, stop.
it's just the square of the intercept.
Yeah, since it's centered at 0, if it weren't centered at 0, it would start to feel a little bit icky, but. Another way of thinking about this is if you are trying to graph a conic section, defining it parametrically using trig, you can get away with some more stuff. Cool? Okay. If we get through this page, you won't have video for notes because tomorrow I was just having, let's really, can we push to get through these so you guys don't have to learn this through a video? Okay. Hey guys, now I've given you a rectangular equation and I want you to write it parametrically. Okay? And for this first one, we're going to write it parametrically if t is equal to x. Okay? So the first equation is x equals t. Y is going to equal what? 1 minus t squared. Lovely. Done. That's it. So you can change any rectangular equation into a parametric equation if you let x equals t. Sometimes we want to define it differently. Do you guys understand what I'm saying here? Okay, sometimes we don't want to define x with t. We might want to define it in some other capacity, and it changes things. But it doesn't change things. All at the same time. Isn't that lovely? All right, so if I tell you, write a set of parametric equations if m equals dy dx at the point x. You guys, what this means is rewrite x and y in terms of m. So m would be the parameter in this case. Before, the previous parameter was t. This time we want m to be the parameter. Okay? And all we know is m is equal to dy dx. Do we know what dy dx is? We can figure it out because this was defined rectangularly, right? So if I tell you y equals 1 minus x squared, are you comfortable with me saying dy dx is negative 2x? Cool. And you know what else is equal to that negative 2x? Dy dx is equal to m. So we could say m equals negative 2x. So now if I want to write x in terms of m, what could I do? X equals negative m over 2. What would y equal? Well, y is equal to 1 minus x squared, yeah? So if I wanted to write y in terms of m, now that I know what x is equal to negative m over 2, y is going to equal 1 minus m over negative m over 2 squared. So y equals 1 minus m squared over 4. Does this feel okay? All right, so now let's graph each of these. So if I do x equals t, y equals 1 minus t squared. Okay? And let's start with just t equals 0. At t equals 0, x would equal 0, y would equal 1. And then it's essentially the parabola. Time's going to go up. And there we go. But if we started with m equals 0 and defined it this way, we're also going to end up with this 1 minus x squared parabola. But it turns out we graph this side. And so what happens is the orientation of this plane curve, the direction of it, is backwards. Do you guys see? Both of them are the same graph. Like, they look different. But we could graph this from t equals negative 2 to positive 2. And if we did negative 2 to positive 2, it would look like this. Same curve, right? And likewise. So even though both of these are y equals 1 minus x squared defined by different parameters, the orientation of the graph changes based on those parameters. Everybody good? Cool, I'm done.